Hi everyone, we are moving on to section 2.2. In section 2.2, we are going to be talking about the graphs of functions. Graphs are a way we can use pictures to represent the formulas that we may have seen in the past. So first of all, a definition. So let's say we have a function. If f is a function. So again, reminding ourselves what a function is, it takes values in a first set, which we call the domain, and assigns every value in the domain something in the range. And each value goes to only one value in that domain. So we can't have a value in the domain going to two values. Kind of like pushing the button on the vending machine, we only get one thing out. If we get two things out, the machine is broken, it's not a function. So here we have a function with domain, which we called A before. Then the graph of f is the set of points. So we're going to be on that Cartesian plane, or set of ordered pairs, points, ordered pairs. That's another name for a point. Okay, so the set of ordered pairs such that, this should be an f of x. So in other words, x is going to be in the domain, the f of x is going to be the output. So that's another way of thinking of that is, in other words, we're going to let y be f of x. So we're going to kind of use those interchangeably. Okay, so if I am going to graph, we'll start with something easy. So f of x equal to 3x minus 2. Another way to think of this is instead of f of x, think of that as y. And we have already talked about how to graph these functions. First of all, you should recognize this as a straight line, linear, because there's only an x value. So it's a straight line, slope of 3, y-intercept of -2. I do want to put a little bit of history on here. F of x is a notation that was actually used by Sir Isaac Newton. You may have heard of Sir Isaac Newton. He is one of the founders of calculus. And he is the one that did come up with this f of x notation, this function notation that we're using. Another mathematician that was also around at the same time of Sir Isaac Newton was a guy called by the name of Leibniz. And he is the one that used this y. And he liked to use y instead of the f of x notation. Students find his notation a little bit easier to work with because we're used to y equaling 3x plus 2 or 3x minus 2. And then remembering this is my x coordinate and this is my y coordinate. In Newton's day, we would have called it x for the input, f of x is the output. But again, we said this was a straight line, y-intercept of -2, slope of 3, so we can go up 3 over 1, connect our dots, and we get the graph of this function. So we can graph functions. Let's do 3x squared plus 2 by plotting points. So in this section, we are going to plot points. In a section or two down the road, we're going to be becoming a little bit better at plotting points, or a little bit better than plotting points, and talk about how graphs are affected with coefficients and things like that. So we'll be shifting them. So here's a function. We're going to plot some points. So in other words, create a little t-table. So we could call x and y, but instead of y, we have g of x. That's the name of our function. So if I just pick some values, and I'm just going to pick a couple. I mean, you could put more if you wanted. I just randomly chose -2, -1, 0, 1, and 2. And we want to plot the points. I'm going to substitute those values in there. So -2 squared is 4, plus 3 is 12, or times 3 is 12, plus 4, plus 2 is 14. I'm getting ahead of myself. Slow down. Substituting in the -1. -1 squared is 1, times 3 is 3, plus 2 is 5. Substituting in the 0. 0, 0 plus 2 is 2. Substituting in the 1, same as the negatives. It's a nice function. And again, the 2 would give me that 14. So I'm going to be off my paper relatively quickly. So -2, 14, so it's up here somewhere. -1, 5, 1, 2, 3, 4, 5. 0, 2, 1. And this we will eventually learn, whoops, I missed, is a parabola. So we get values that look like that. So there's my 3x squared plus 2. Okay. I want to ask a question, and I'll write it down here. How can we tell? Let's say I don't have the equation, but I'm looking at a picture. How can I tell if a graph represents a function? So let's look at a couple of graphs and determine, do we have a function or not? So let's just, I'm just going to draw some pictures. I don't know, there's a picture of a graph. You know, let's do a circle. Let's do a couple other ones. Here's our V piece that we've seen before. Let's look at this guy, something that looks like that. So there's some functions, or graphs. I shouldn't say functions. These are graphs. Are these functions? Now there's a couple of rules for functions, and we will assume that, like on this guy, you know, the domain this does not include these, or the domain does not include the values that we don't get pictures for. But are they functions? The answer to that kind of makes, we have to go back to the definition of a function. For every input, we get only one output. So our inputs are all these x values. So the x values. Do we get one output? So in other words, if we have like this one, here's an input. My output here and here. Those are the values that came out of that expression. Since this input has more than one output, this is not a function. This one here has two outputs for this input. It is not a function. These, here's an input. I have an output, one output. Here's an input, one output. These are functions. So how can we tell? The rule is if it passes the vertical line test. Vertical line test. If you have a graph and you can put a vertical line through any part, so vertical lines go up and down, and it only crosses the graph one time, it will be a function. Here, they pass more than one time, so it is not a function. So that's an easy way to tell if a picture or a graph or of something if it does represent a function. I'm going to stop this video right now. I am going to come back and finish section 2.2 in a second. But before I do that, I do want to show you some common graphs that we'll be seeing. So I want to kind of bring these up. These are in the textbook. I did pretty much just copy this page from the textbook. And here's some functions and their graphs. And I kind of want to look at them. Here's our linear functions, straight lines. Those are functions. A vertical line would not be a function because it would not pass that vertical line test. These are considered our power functions, so x to a power. Here's our basic x squared and x cubed. What happens as x, that n increases? So as the power increases, our even ones are all going to look similar to this x squared, except they're going to get flatter on the bottom. And as we increase the power on an odd function, it will look very similar, but they'll get steeper on the ends and flatter in the middle. Here is our root functions. Here's our even roots. So again, they're kind of getting flatter in this middle piece as we increase. Even roots, we can only take even roots of positive values. So this is your square root, your fourth root. These are your odd roots, your cube root, your fifth roots. Here's some reciprocals. 1 over x squared. Very similar as we increase those powers. I'm going to come back to this one in the next video, this integer function, this greatest integer function. And this is your absolute value function that we've seen, the v. So here are some common functions that we're going to kind of start working with as we get into later sections in this chapter. But I want you to kind of be aware of what they look like.